Calculus is one of the most powerful mathematical tools ever developed because it explains how things move, grow, and change over time. In the real world, almost nothing remains constant. Planets move through space, populations grow and shrink, temperatures rise and fall, and objects accelerate and slow down. Calculus was created to understand these continuous changes. Developed independently by Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century, calculus became the mathematical language used to describe motion, natural processes, and dynamic systems throughout science and engineering. At its core, calculus is built onto major ideas: derivatives and integrals. A derivative describes how something changes at an exact moment. It measures the rate of change. For example, when a car is moving, its position changes over time. The derivative of position with respect to time gives velocity, and the derivative of velocity gives acceleration. This idea allows scientists and engineers to analyze how objects move, how quickly they speed up or slow down, and how forces influence their motion. Without calculus, it would be extremely difficult to precisely describe the motion of rockets, satellites, or even vehicles on Earth. This concept of motion was fundamental to the work of Isaac Newton when he developed the laws of motion and universal gravitation. Using calculus, Newton was able to explain how objects accelerate under forces such as gravity. Calculus allows physicists to predict the trajectory of a projectile, determine the orbit of planets, and analyze complex systems like weather patterns and fluid flow. It provides a mathematical framework that connects motion, force, and time into one coherent system. Calculus also plays a central role in understanding growth and decay. Many natural processes grow in ways that are not linear. Populations increase, bacteria multiply, investments accumulate interest, and radioactive materials decay. These processes are often modeled using differential equations, which are equations that describe how a quantity changes over time. For example, in population dynamics, calculus helps scientists predict how quickly a population will grow based on birth rates, resource limits, and environmental conditions. Similarly, in finance, calculus helps model compound interest, risk, and market changes. Another powerful application of calculus is understanding accumulation. This is where integrals become important. If derivatives measure how fast something is changing, integrals measure the total accumulation of that change. For instance, if you know the velocity of a moving object at every moment, integration allows you to calculate the total distance it has traveled. In physics, integrals help determine quantities like work, energy, and electric charge. In economics, they help estimate total cost, revenue, and consumer demand over time. Calculus is also essential for modeling complex systems where many variables interact simultaneously. Weather forecasting, climate modeling, and biological systems all rely on calculus-based equations. These equations describe how temperature, pressure, humidity, and other variables interact dynamically over time. Supercomputers use numerical calculus methods to simulate these systems and produce predictions that help scientists understand and respond to global changes. In modern technology, calculus operates behind the scenes in countless innovations. Computer graphics use calculus to simulate motion and realistic surfaces. Machine learning algorithms use calculus to optimize models and minimize errors during training. Engineering disciplines rely heavily on calculus to design bridges, aircraft, and electronic systems. Even medical imaging technologies, such as CT scans and MRI reconstruction algorithms, rely on calculus-based mathematics to produce detailed images of the human body. Perhaps the most profound aspect of calculus is that it provides a universal language of change. Whether studying the motion of galaxies, the flow of rivers, the growth of economies, or the spread of information through networks, calculus offers a way to describe continuous change with precision. It transforms complex natural processes into mathematical models that can be analyzed, predicted, and understood. Ultimately, calculus reveals that the world is not static but constantly evolving. Every movement, every transformation, and every growth pattern can be understood through the mathematical relationships that calculus describes. By capturing the mathematics of motion, growth, and change, calculus allows humanity to explore the universe, build advanced technologies, and uncover the hidden patterns that shape reality itself.